Hello friends, in this lecture we will cover the next type of sensor or next type of transducer, that is LVDT. Now learning outcomes. Now after studying the LVDT, students will be able to understand or students will be able to explain first what is LVDT, then next which are the different advantages of LVDT, then which are the different disadvantages of LVDT, and which are the different applications of LVDT. Now LVDT stands for Linear Variable Differential Transformer, or you can also call it as an Linear Variable Differential Transducer. Now LVDT is a passive type of transducer. As we know, the basic difference between active type of transducer and passive type of transducer. For the operation of active type of transducer, we doesn't require any external power supply for its operation, but for the operation of your passive type of transducer, we require the external power supply for its operation, and for the operation for the LVDT, we requires the external power supply for its operation. That's why LVDT is called as a passive type of transducer, or it is a passive type of transducer. Now LVDT is an absolute measuring device that converts the linear displacement into electrical signal through the principle of mutual induction. Means the input physical quantity for the LVDT is the displacement, and this displacement will be converted into the electrical signal by using the principle of mutual induction. Means the input measurand or input physical quantity for the LVDT is the displacement, and the output of your LVDT will be converted into what? Electrical signal. Means displacement is going to convert into electrical signal through the principle of mutual induction. Now before going to the operation of your LVDT, first of all see the construction of LVDT. Now first figure indicates the construction of LVDT. As LVDT is a variable inductance displacement transducer, means displacement is going to convert it into what? Electrical signal. That's why at the middle one metallic core is present, and there will be displacement of this core at center or at right or at left. Means the displacement of core is totally depends on how much pressure you are going to apply. Means the LVDT is a variable inductance displacement transducer, and it consists of one primary windings and two identical secondary windings, that is secondary winding 1 and secondary winding 2, and these two windings, that is secondary winding 1 and secondary winding 2 and primary winding, are axially placed and wound on a cylindrical coil former, and a rod shaped magnetic core is positioned centrally inside the coil assembly, and this rod provides the row reluctance path for the magnetic flux which links the coils, that is windings, and the moving object, the displacement of which is to be measured, is coupled to this movable rod, and the two secondary windings are connected in series opposition. Means the connection of your the second figure, that is connection of LVDT windings, shows the connections of two secondary windings. Now these two secondary windings are connected in series opposition, therefore the voltage induced in these windings are of opposite polarities, and the output voltage is given by, that is EO, which is equals to EO1 minus EO2, where EO1 is the EMF induced in secondary winding 1 and EO2 is the EMF induced in secondary winding 2. Now the operation of LVDT. Now to understand the operation of your LVDT, we are going to consider total number of 3 cases. Now first case, that is case number 1, when the position of core is at center. As we know, your final equation, that is final EMF, which is final induced EMF, which is directly proportional to your output voltage, means EO, which is equals to EO1 minus EO2. Now if the position of core is at center, now when the core is at center of the coil, then the equal amount of flux gets linked to the both secondary windings, that is secondary winding 1 and secondary winding 2. Means the flux will link to the both the secondary windings will be equal. that is EO1 equals to EO2, means EMF induced in both the secondary windings, that is secondary winding 1 and secondary winding 2 will be equal, that is EO1 equals to EO2. Now due to equal flux linkage, the induced voltage in both secondary windings are equal, but they have opposite polarities, means EO1 equals to EO2, but both have opposite polarities, means EO1 is positive and EO2 is negative. That's why the output voltage of LVDT, that is EO, will be equals to 0, as EO1 equals to EO2. Means the conclusion for case number 1, when the position of core is at center, then the EMF will induce in both the secondary windings will be equal, that is EO1 equals to EO2. As EMF induced in both the secondary windings is equal, so the output voltage, that is EO, which is equals to 0. Now case number 2. Now when the position of core is at right. Now when you apply pressure to the core, then please assume that the position of core is at right, means at the secondary winding 2. Now when the core is displaced from its null position towards the right. Now what is null position? Null position is nothing but what? When the position of the core is at center or is at middle of the secondary winding 1 and secondary winding 2, then that position is called as a null position. Now the case number 2, when the core is displaced from its null position towards the right, then the EMF induced in secondary winding 2 will be higher than that of your EMF induced in secondary winding 1, means EO2 is greater than that of your EO1. So the output voltage will be negative. Now why output voltage is negative? As we know, your output voltage, that is EO, which is equals to EO1 minus EO2, but when the position of the core is at right, then the EMF induced in secondary winding 2 is greater than that of your EMF induced in secondary winding 1, means EO2 is higher as compared to EO1. That's why your EO or your output voltage will be negative. Now this will be your case number 2. Means what is your conclusion from for case number 2? When the position of core is at right or is at secondary winding 2, then the total EMF induced in secondary winding 2 is greater than that of your secondary winding 1. So your output voltage will be negative, as our equation output voltage, which is equals to, that is EO, which is equals to EO1 minus EO2. And for this case, EO2 is greater than that of your EO1. That's why the output voltage, that is EO, will be negative. And third case, if you release the pressure to the core, then assume that your position of core is at left from the null position. Now when the core is displaced from its null position towards the left, then the EMF induced in secondary winding 1 will be higher than that of the EMF induced in secondary winding 2, that is EO1, which is greater than that of your EO2, where EO1 is the EMF induced in secondary winding 1 and EO2 is the EMF induced in secondary winding 2. So the output voltage will be positive. Now why output voltage is positive? For this case, when the core is at left position or when the core is at secondary winding 1, then total EMF induced in secondary winding 1 is greater than that of your total EMF induced in secondary winding 2. Means EO1 is greater than that of your EO2, and as our output voltage equation, that is EO, which is equals to EO1 minus EO2, and for this case EO1 is greater than that of your EO2, that's why your final EO or your output voltage for this position will be positive. Now transfer characteristics. Now the transfer characteristics indicates means first of all, the transfer characteristics is a graph of the core position versus the output voltage, that is EO. Now if you see the first position, when your core is at secondary winding 2, means when your core, the position of your core is at right, means first construction. Now when the position of the core is at secondary winding 2 or it is at right, then your output voltage, that is EO, which is negative. Then next, when the position of the core is at middle, when the position of the core is at middle, then the EMF induced in both the secondary winding, that is secondary winding 1 and secondary winding 2 will be equal. That's why your EO1 which is equals to EO2. So your output voltage will be equals to 0, and this position is also called as an null position. Similarly, third position, if the position of the core is at left or the position of the core is at secondary winding 1, then what will happen? If the position of the core is at secondary winding 1, then your EO1 will be greater than that of your EO2. So your finally your EO will be positive. As we know, EO which is equals to EO1 minus EO2 means your final output voltage will be positive. Means the transfer characteristics for this position indicates your output voltage is positive. Similarly, when your core is at middle, then your transfer characteristics indicates your output voltage which is equals to 0. Similarly, when the position of the core is at right, then that indicates your output voltage will be negative. Now, which are the different advantages of LVDT? First, very fine resolution. Then second, high accuracy. Then third, very good stability. Then next, it is easy to fabricate and installation. Then next, it can operate on high temperature. These are the advantages of LVDT. Now, which are the different disadvantages of LVDT? First, it is sensitive to the external magnetic field. Then second, complicated circuitry is needed. And third, due to mass of the core, the LVDT is not suitable for the measurement of fast displacement. Means if the displacement of the core is fast, then it is not able to measure the fast displacement by using your LVDT. Now, which are the different applications of LVDT? In addition to the displacement measurement, the LVDT is used in measurement of pressure, then next measurement of load, then next in measurement of force or weight, etc. Now let's see one application of LVDT, that is LVDT type pressure transducer. Now here the first pressure is applied to the diaphragm. Now in this figure, your diaphragm is a primary transducer which will convert the pressure into what? Displacement. Means the pressure is applied to your diaphragm. When you apply the pressure to the diaphragm, then there will be movement or there will be displacement of the core, and the displacement of the core is totally depends on how much pressure you are going to apply. Now when you apply the pressure, then there will be movement of the core. Means in this figure, your diaphragm is a primary transducer which will convert the pressure into what? Displacement. Then the displacement of core will be converted into output voltage, and this output voltage will be directly proportional to the pressure. Means your output voltage is totally depends on, yes, how much pressure you are going to apply. Now when you apply maximum pressure, then your output voltage will be maximum. When you apply minimum pressure, then your output voltage will be minimum. Thank you.